All right, a beautiful introduction to proofs using the limit theorem. Okay, so what we're going to look at is a few things with limit theorems and proofs. We're not going to get too deep into the proofs, just a few more basic examples. Okay, so the idea, I've kind of outlined the steps that you want to do if you're going to do an epsilon delta proof. You want to find delta. You have to kind of do some scratch work to find delta. You're going to let epsilon be an arbitrary positive number. You're going to use this inequality to find a condition of this form where delta depends on only the value of epsilon. Then we're going to write a proof. So I'm going to kind of outline the scratch work first of all. So we're going to try to prove this limit is correct. And by the way, it's not sufficient to just go, well, let's plug in 4 and go 4 times 4 minus 15 equals 1. Proved. Okay, that doesn't prove anything. That proves you know your arithmetic, and that's it. Okay, so first thing we're going to do is we're going to formulate these things. So first of all, let's formulate this, and let's formulate this. We're going to try to find a connection between epsilon and delta. And you kind of do this on the side, just kind of scratch work. So let's see. First of all, a is 4 in this problem, so we're going to say we have 0 less than x minus 4 less than delta. And then we're going to do this. We take the function, which is this, and then we take the value of the limit, which is 1. Okay, so f of x is that part, L is that part, A is that part. Okay, so we're going to formulate the function, 4x minus 15 minus the value of the limit. We're going to set that less than epsilon. So that will give 4x minus 16 less than epsilon. And see, what you're trying to do is you're trying to look at a connection between this and this. And the connection's not too hard on this one. You can factor a 4 out of this, and then you would have this. And then you can take an absolute value. I mean, technically, if you have a product of two expressions in an absolute value, technically you're allowed to do this. So you would get 4 times this value right here. Okay, now what I'm going to do is I'm going to divide both sides by 4. So what I get is I get x minus 4 is less than, not less than or equal, but less than epsilon over 4. Okay, so now I've established the connection. It's pretty clear what that connection is. Okay, so if you look at this, the connection between the two is these things have to be the same because we got these things the same. So what the connection is delta needs to be the same as epsilon over 4. So that's the connection we're trying to find. You do that with scratch paper. Now we're going to formally give the proof. Okay, and then the proof has to be, the steps got to be written in a certain way. So the first thing we're going to do is we're going to let epsilon be just some positive number. And we're also going to let epsilon be equal to, or hold on, not epsilon, we're going to let delta, we're going to let delta equal epsilon over 4. Then we can start writing our proof. Okay, so we're going to make this assumption. We're going to assume this part. We're going to assume that delta is a greater zero. It is some positive number. Delta is a positive number. So we're going to assume that x minus 4 is greater than 0 is less than delta. Okay, so now we're ready to just sort of write out the steps of our proof. So we're going to say, then we can conclude from this that x minus 4 is less than epsilon over 4. Okay, And then what we can do is we can multiply both sides, okay, like this. So we can make that conclusion now. Now what we're going to do is we're also going to say that we're going to do the f of x part right there. So we're going to do 4x minus 15 minus 1. We know that that is less than epsilon. Okay. And then what we're going to have is 4x minus 16 is less than epsilon, like that. And then we can go ahead and factor that 4 out, so we get 4 times the absolute value of x minus 4 is less than epsilon, like that. Okay, then we can, from this conclusion, what we can go ahead and do is this. Okay, you can go ahead and take this now, and you can multiply both sides by 4. So we can say, therefore, 4 times x minus 4 is less than epsilon over 4 times 4. So then that would give the result 4 times x minus 4 is less than epsilon. Okay, so we have proved that this leads to this then. Okay, so we have proven the theorem by doing that then. Okay, we have taken the assumption and showed by letting delta equal epsilon over 4 that we can now draw the conclusion from this assumption to this part right here. So that would be one way that you could write your proof. Okay. Okay, on this next proof, this one is actually very similar to that. Again, what we have is, this is your function, this is the value of the limit L, and that's the value of A. Okay, so when you're looking at this limit definition, what you're doing is, the first thing you're doing is x minus a less than delta. So we're going to have 0 is less than x minus 1 less than delta. And then we're going to try to establish a connection between f of x minus L less than epsilon. Okay, so what we have is f of x is 8x plus 5, minus L is 13. So that will give 8x minus 8 less than epsilon. You can factor out the 8 to get x minus 1 less than epsilon. Then you can do the absolute value of 8, so that will come out of the absolute value, so you get this. Okay, so you're trying to establish this connection. So you see here that those expressions right there, the x minus 1 is the same. So if I go through and divide both sides by 8, I get the expression I'm after. I get absolute value of x minus 1 less than epsilon over 8. So that means since this and this are the same, then therefore these things are going to have to be the same. So we're going to have to say we're going to let delta equal to epsilon over 8 when we write in our proof. Okay, so our proof just always kind of goes like this. You want to just kind of formally say these things. You want to say let epsilon be some positive number greater than 0, and then we're going to assume that 0 is less than, you also want to let delta be a positive number, and you want to assume that x minus 1 is less than delta. Okay, so you're going to try to establish this connection on this then. So we're going to prove, what we're going to prove basically on this, and I need to write this like this. What we're going to do is we're going to prove that f of x, 8x plus 5 minus 13 is less than epsilon. So that's what we're going to prove, okay? Or, more specifically, that would be 8x minus 8 is less than epsilon, or more specifically, 8 times absolute value of x minus 1 is less than epsilon. So that's what we're trying to prove, okay? So what we do is we just write this down then. So, okay, we can say we have 0 is less than x minus 1 less than delta, and then we can now let delta be epsilon over 8. Okay, so then what we would have is, we can just write this as x minus 1 is less than epsilon over 8. Okay, then we can multiply both sides by 8. If we do this, okay, and then therefore what we end up with is we end up with 8 times x minus 1 is less than epsilon. So that would prove the theorem. That's a good way to write that limit proof out, is using those kind of steps like that. Okay, and then the next one, again, we're going to do a very similar thing. Again, with this one, you want to realize that's a, that's f of x, and that's the value of the limit. Those are the key things. So what we're going to have on this is we're going to, first of all, formulate this part of the limit definition. So we're going to have 0 less than x minus 3. Let me zoom on that just a little bit there. So we're going to have 0 less than x minus 3 less than delta. Okay, now what we're going to formulate is the distance between f of x and L is less than epsilon. So f of x is negative 2x plus 8. The value of the limit's 2. Okay, so that will give negative 2x plus 6 less than epsilon. We can now factor a negative 2 out, so we'd have this. Okay, you can take the absolute value of negative 2 out, so you would have 2 times x minus 3 less than epsilon. And then you could divide by 2, so you would get x minus 3 is less than epsilon over 2. So if you take this statement right here, where you have 0 is less than x minus 3 less than delta, then since these things are the same, then these things have to be the same. So what we're going to do is we're going to, in our proof, we're going to let delta be equal to epsilon over 2. Okay, so now we're ready to formally write our proof. The steps are pretty similar, like this. What we're going to do is we're going to let epsilon be a positive number. We're also going to let delta be some positive number. And we're going to assume this part. You always assume this part. So we're going to assume that 0 is less than x minus 3 is less than delta. And then you're going to try to prove this part. Okay, so we're going to prove this part. So we're going to prove that negative 2x plus 8 minus 2 is less than epsilon. And then you can go ahead and, make a few algebraic simplifications. That's negative 2x plus 6 is less than epsilon. You can factor the negative 2 out of that to get this. Okay, you can take the absolute value of negative 2 to get 2 times absolute value of x minus 3 less than epsilon. So that's ultimately what you're trying to prove. And then what you can do now is we can let delta be equal to epsilon over 2. Okay, so what we're going to say is we have, this is the assumption we make, we have 0 is less than x minus 3 is less than delta. So then what we get is we get 0 is less than x minus 3 is less than epsilon over 2. Okay, like that. Then what we can do is we can multiply both sides by 2. And I'm just going to ignore the 0 part because I've got that established. So I'm going to multiply both sides of this inequality by 2. So that will give us what we're trying to prove. We'll have 2 times x minus 3 is less than epsilon. Okay, and basically that's what we were trying to prove. We tried to prove that this is true given the assumption we make. So that would close off the proof. That's a good way to write that proof. Okay. Okay, so that's how that would go. Those are pretty straightforward limit proofs. And now we're going to go on and look at this next one, number 21. Okay, so with this one, again, you're going to start off with 0 less than x minus a less than delta. And then you're going to do f of x minus L less than epsilon. And again, you're trying to establish a connection mathematically between delta and epsilon. Okay, so when we start this, we're going to have 0 less than x minus 4 is less than delta. And let's go over and formulate this thing then. So we're going to have the function x squared minus 16 over x minus 4 minus the value of the limit 8 less than epsilon. So it looks like we need to do some factoring. That's a difference of two squares. So we're going to factor x plus 4, x minus 4 over x minus 4 minus 8 is less than epsilon. Okay, that'll cancel that out. That will give x plus 4 minus 8 less than epsilon. And then that will lead us to x minus 4 is less than epsilon. So if you look at these things, see, we've got these things are the same. And that's what you're always trying to do. So that just means that delta and epsilon have to be the same. So in our proof, we're going to let delta be epsilon. Okay, so when we formally write our proof now, the formal written proof will look like this. Okay, the first thing that you want to do on this is you want to let epsilon be a positive number and you want to let delta be a positive number by definition. And then you're going to assume this part. You assume this part of the definition, okay? So you're going to assume that 0 is less than x minus 4 is less than delta, okay? So now we're going to establish the connection. So we're going to try to prove this. We're going to prove that the absolute value of x squared minus 16 over x minus 4 minus 8 is less than epsilon. And we'll go ahead and do some of the simplification within our proof. So we have x plus 4, x minus 4 over x minus 4 minus 8 is less than epsilon, which will give us now, after you cancel that, you're going to have x plus 4 minus 8 less than epsilon. And then just sort of moving this proof over here, I'm going to have x minus 8 less than epsilon. So that's what we're trying to prove, okay? So then what you would say is you would say, let's let delta equal epsilon, and then we can say we have, from our assumption, 0 less than x minus 4 less than delta. So therefore, we would have x minus 4 less than epsilon, and that's what we were trying to prove anyway, okay? All right, now I did make one mistake in writing my proof. This right here, 4 minus 8, should have been minus 4. So that need to erase that and change that to a 4, okay, like that. So what you did is, see, you were trying to prove this. That's what you were trying to prove. And then just by taking the assumption and letting delta be epsilon, you have the proof. So that would be the steps of how you'd write that proof. Okay? Right, the next one should be fairly similar in the way it's written. And again, let's kind of make the connection over at the side. So the first thing we look at is 0 is less than the difference between x and a less than delta. So a is 3 in this problem, so we're going to start with 0 is less than x minus 3 is less than delta. And we're going to try to look at the connection between f of x minus L less than epsilon. So we're going to definitely have some factoring going on this like the last problem. So we're going to say x squared minus 7x plus 12 over x minus 3 minus the value of the limit. The value of that limit's -1, so you say minus -1 less than epsilon. Okay, it looks like we can factor this trinomial as x minus 3, x minus 4 over x minus 3. That will become plus 1 less than epsilon. That will cross out, leaving us with x minus 4 plus 1 less than epsilon. So that will leave us with x minus 3 is less than epsilon. So again, if you look at this and look at this, they're the same. So that just means delta and epsilon have to be the same. So in our proof, we're going to let delta be equal to epsilon. We have established the connection. Okay, so when we formally write our proof, we write it like this. First thing is you always want to start by saying let epsilon be greater than 0 and let delta be greater than 0. You're always going to assume this part. You're trying to prove that becomes this. Okay, so we're going to assume that 0 is less than x minus 3, and then that's less than delta. Okay, and what we're going to try to prove ultimately is that the function x squared minus 7x plus 12 over x minus 3 minus negative 1 is less than epsilon. So we just kind of write out the steps like this. Okay, so we would end up getting, when you factor this, you would have x minus 3 times x minus 4 over x minus 3 plus 1 is less than epsilon. Okay, that would lead to x minus 4 plus 1 is less than epsilon, which would end up with x minus 3 is less than epsilon. So that's what you're trying to prove. So then you could say we have the assumption 0 less than x minus 3 is less than delta. And then we want to state that we're going to let delta be equal to epsilon. Then what we would have is we would have, from this assumption, we would have x minus 3 is less than epsilon. Okay, and that would prove. So this is what we're trying to prove. This is how we proved it right there. Okay, so that would be the proof of that. Okay, so that's how that would go. And let's look at a couple more proofs to close this off. Okay, on this next one, we're going to, again, start off like we're used to doing, as we do x minus a less than delta. And then we're also going to work with f of x minus L less than epsilon. Okay, so if we start this, a is 0, so we would have 0 less than absolute value of x minus 0 less than delta, or this. So that's going to be a part we're going to assume. Now we need to go over here and make a connection. Okay, so the function is x squared. The value of the limit is 0 less than epsilon, so that's going to give us absolute value of x squared less than epsilon. Now, since we're squaring a number there, if x is any number, negative or positive or 0, we don't really need the absolute value, so we just end up with this. Okay, so what we're trying to do is establish the connection between these two. If I take a square root of both sides, I would end up with, and we have an identity that says the square root, anytime you do a square root, you're going to get either 0 or a positive number, so we can write that as absolute value of x less than epsilon. So now if you look at this and this, we've got that the same, so that just means what we're going to do is we're going to let delta be equal to the square root of epsilon when we write our proof. Okay, so when we formally write our proof, it's going to go like this. We start by saying let epsilon be a positive number. We're also going to let delta be a positive number. And we're going to assume that the absolute value of x minus a is 0, is less than delta. So we're going to make that assumption, okay? So we're going to try to prove this. We're going to take the absolute value of the function x squared minus the value of the limit 0 is less than epsilon. So that's what we're going to try to prove. So from here we can simplify and we would get x squared is less than epsilon. We can conclude that the absolute value of x squared is just x squared. So that will give x squared less than epsilon. Okay, then we can do the square root of both sides. Okay, so we would end up having this. And then we don't just say x, we have to say absolute value of x on that, because if x was a negative number, we get positive numbers when we take a square root. So we're going to now conclude that absolute value of x is less than epsilon like that. Okay. Then over here we can continue by saying we have 0 less than x minus 0 less than delta. And from there we would have 0 less than absolute value of x less than delta. Then we can let delta be equal to the square root of epsilon. So therefore we would have 0 is less than absolute value of x. is less than square root of epsilon. And see, this is what we were trying to prove, so we just proved it. Okay, just by letting delta be equal to the square root of epsilon. Remember, we're trying to find a delta that will fit within the delta band around the value A. Okay, and we're going to do one more, which is fairly similar, and then that will be the end of the proofs that we're going to do. So this one's going to have a similar kind of structure to it. So again, we're going to start with 0 less than x minus a less than delta, and then we're going to work with f of x minus L less than epsilon and try to establish connection. A is 3, so we're going to have 0 is less than x minus 3 is less than delta. That's what we're going to work with. Now let's establish the connection. So the function is x minus 3 to the second. The value of the limit is 0 less than epsilon. Okay, so that's going to leave us with x minus 3 squared is less than epsilon. Again, if we take the absolute value of an expression being squared, since this thing is always positive, then we could just write this now like this. We could just square root both sides. Really, we really don't need that absolute value, so we can just write this as x minus 3 squared is less than epsilon. Okay, then we can do a square root of both sides. Again, we're trying to make this look exactly like that. So that would give us, with absolute value of x minus 3 is less than square root of epsilon. So since we've made these two things the same, that means the connection is these things have to be equal. So what we're going to do in our proof is we're going to let delta equal the square root of epsilon. Okay, then if we formally write our proof, it'll go like this. Okay, so what we're going to do is we're going to start by letting epsilon be a number greater than 0. We're going to let delta be a number greater than 0. And we're going to assume the part where we have 0 is less than x minus 3 is less than delta. That's the first part. And what we're going to try to prove is that the absolute value of the function, x minus 3 squared minus the value of the limit, is less than epsilon. Okay, now we could go ahead and simplify in our proof. That's going to give absolute value x minus 3 squared less than epsilon. Okay, the absolute value is not really necessary because that's going to be a positive number or 0 anyway. So we have x minus 3 squared less than epsilon. I can do the square root of both sides. And when I do the square root of both sides, what I'm going to end up with is the next step is, this is absolute value of x minus 3. You've got to have that because you're doing a square root. You're getting a positive number. You know, if there are times when x could be a negative number. So in order to guarantee that you get a positive out of that square root, you got to have the absolute value. Then we have this, okay? Then we can say we have what we assumed was 0 less than x minus 3 less than delta. That's part of the definition, okay? And then all we really need to say is let delta be equal to the square root of epsilon. Then what we'll have is x minus 3 absolute value, replacing delta with square root of epsilon. We've proved what we were trying to prove. So that's it. Okay, so what we're trying to do in this section is give Calculus 1 students an idea of how proofs are written. These are kind of the more basic variety that we're going to do. It helps students when they get into higher levels to do this. If somebody's going to study mathematics in depth as a major, you'll take a class generally in a senior year of a math major program called Real Analysis. And the proofs get very technical. You're doing a lot of proofs and you're looking at the theory behind calculus. And that comes in handy for those students. But also, as you run through a calculus sequence, your teachers are going to, from time to time, do proofs in class. So you want to be able to follow what they're doing. And math textbooks get more and more technical as you get to higher levels. So you want to start getting into this technicality a little bit to help you understand the calculus. Okay, so that should wrap us up. This is kind of an overview of the diagram that we were talking about is with this is basically epsilon's a positive number centered around the value of the limit. This kind of gives you an epsilon belt, and then you can find a delta that will fit within that range. So the idea is this is the value of the limit. You're doing a limit as x approaches a. That'll give you the value of the limit. And then as you close in, as epsilon gets closer and closer to zero, epsilon's going to approach zero, then you'll still be able to find a delta that will fit within that delta belt. So that's the idea. Okay, so I hope that helps you to understand these proofs at this level.